Okay, guys, let's continue with the remaining of this chapter, extrusion-based systems we were talking about. We discussed the fundamental steps of this operation. We were discussing the liquefaction. After we extrude the material that is liquid or solid, we need to somehow, or liquid or semi-solid, we need to solidify it completely. And for these purposes, we usually use some kind of fence. And so we have a forced, let's say, convection. And for the heating purposes, as I've shown you in this on this printer, we have some kind of heaters, and this is mostly done with other extrusion-based systems. They have a heater at this tip, and they also need to measure it by using probably thermocouples, and in their controller, they usually have a PID controller try to control this temperature at the defined value. Since if you do not control it properly, if it's oscillating, if the temperature is oscillating, then you will have some extra material on the part, on the table. So it's highly important to control the temperature at the defined value. And this temperature value depends on the type of material you are extruding. And for instance, if you are using a soluble support structure, which we use in this gyrotin, the melting temperature is usually around 60. So for the water-soluble material, the heating is not working too much. The temperature is around 60, but for such PLA or ABS materials, it's around or more than 200 degrees. Obviously, if you increase the chamber, the size of the build chamber is more, then you'll be able to control its difficulty. It will not be easier. So for photopolymers, this temperature is much lower, and for thermoplastics, it's, as I said, around 200 degrees. So now let's jump to the main step, the extrusion step. So the nozzle, the shape of the nozzle and the size of that shape actually is important in terms of the shape, since the extruded material will be taking the shape of your nozzle opening. So if you have a larger nozzle diameter, then as we mentioned in the first hour, the resolution of your part will be very low. So you cannot actually print or extrude features which are smaller than the nozzle diameter or the nozzle size. And the thing is that since we are using pressure, lots of material at the backside, we can easily use such extrusion-based systems for printing or fabricating large products. We also have some wide area or large area additive manufacturing. It's abbreviated as LAAM. They are printing even some cars, some boats, having sizes of some meters, and they can only use extrusion-based systems. Even consider some structure or building printing systems. They are all using extrusion-based systems. You will see some examples in the upcoming slides. But what do you think? What about the smaller parts? We mentioned them on Tuesday. What kind of systems we should use for smaller parts? And volunteer for the answer?
Laser-based systems.
Laser-based and photopolymer systems. If the diameter of the focus diameter of your nozzle is very low, let's say around some micrometers, then you can obtain such very small parts having detailed features. And obviously, the extrusion we are using on additive manufacturing is not exactly the same as the one we are using in hot extrusion or cold extrusion in conventional manufacturing operations. We don't have a conventional screw mechanism, Archimedean screw. We have pressure actually generation at the back side, and with the help of the pressure drop, we can extrude material, and this extrusion depends on the nozzle geometry and as well as the material viscosity. And you know that this viscosity depends on temperature. By increasing the temperature, you can decrease the viscosity. And this is the conventional Archimedean screw. This is kind of a cross section, and this image is from our textbook. The material flows actually through these openings. And we have also seen the example in 3DO. They were using again a kind of a screw for the generation of filaments. And we need to have pressure actually for the flow, and we have the pressure needs actually for the flow of material, and also we need to have some pressure for the drag. We have friction on the walls. We need to overcome them so that material will be extruded. And if you want to do a kind of a modeling for the pressure, obviously you need to also consider the gravity in account. If it's a vertical one or vertical one or the horizontal one, you may maybe neglect the effect of gravity. And this was another step in the extrusion-based system, the solidification. We said that in order to retain the shape of the extruded product, it should be solidified as soon as possible. And if it's a proper solidification, then you will have better dimensional accuracy and it will satisfy the dimensional requirement of the user. And sometimes the gravity actually plays an important role, especially if it's an overhanging region or a shallow angle for the surfaces. With the help of gravity, you will lose some accuracy. Another thing is surface tension. So you should be also aware of that issue while doing some maybe modeling in the solidification part. Another issue is that the shrinkage. Since we are printing or extruding these materials at usually high temperatures, once they cool down to, let's say, room temperature, their size will decrease. They will shrink, and we will have some thermal stresses. The size will be not exactly the size we are printing at that moment. It will be a bit lower, less than the initial size. So if it's a critical application, if the dimensional accuracy is highly important for you, then you should also consider shrinkage. So what do you know? What is the easiest solution actually to overcome this shrinkage phenomenon? Can anyone tell me the easiest solution?
Heating the base of the printer.
Can you tell again?
Heating the basement layer of the printer.
No.
Drafting.
No.
Make the part bigger.
Yeah, that's the simplest approach. Since if the part is shrinking from all the dimensions, from all regions, then you may print a bit larger, maybe around 1%, 2% larger. Then once it shrinks, it will be at the same dimensions actually you like. Another issue, if you don't have an actually proper cooling, so if you remember our case, we have a fan left-hand side, on the right-hand side, we have another fan at the front. So we are trying to make it as uniform as possible, but if the cooling is not uniform, then probably you will have some distortions and some stresses will develop inside the part, and even they may cause some cracking. So how can we overcome this? We can solve this problem by having less temperature differential actually between the chamber and between the part. But if you look at our printer, this is not the case. We don't have a closed chamber here. It's open to environment, open to the room. So we are not actually controlling the temperature in this printer properly. So I cannot say that we can eliminate this thermal problems on this printer. If it's an important issue for you, then what you need to do, you need to cover this side, the upper side with some extra equipment so that the temperature inside this, let's say, chamber is controlled and you don't have much temperature difference between the extruded part and the chamber. So if that's the case, then that means you will develop less thermal stresses and you will have no crack on the part. Any questions, guys?
Hocam bu shrinkage'in ne kadar olacağını ölçebilen bir sisteme sahip miyiz şu anda?
Not exactly, but for thermoplastics, if it's PLA, it's usually around 1%. If it's an ABS material, we will discuss in a moment, it's in maximum 3%. And another thing is that it's not uniform. You cannot say that it's shrinking from right-hand side 3% and from left-hand side 3%. It may be different. It depends on also the shape of your product. So it's not easy to determine, but there are some studies on such modeling, shrinkage modeling, but they're not completely successful.
Teşekkürler hocam.
Welcome. So we said at the beginning, in extrusion-based systems, we need to do the position control, especially on the XY plane properly. And we may use very simple platforms, and our head will be moving on that platform usually, but there are also different versions. In some cases, head might be stationary, the X and Y movements might be obtained with help of the movement of the table. It's also possible, but usually we have a fixed table and the head is moving. And in that control, the acceleration of that head is highly important. Since if you do not accelerate properly or decelerate properly, you may have some extra materials again on the layer, and this will obviously decrease the quality of your overall product. And this will happen actually mostly at the corners of the head. And we usually make use of some planar plastic systems. We may have two types of linear drives. The first one is, as in our printer, we may use belts directly, or we may use lead screws. In the Z-axis, if you remember, we were using a kind of a lead screw, but for the X and Y, we are using belts. Why is that? Since it's much, much cheaper than the lead screw. So that's why for such desktop printers, we prefer to use belts. But for professional ones, professional FDM type of printers, people are using lead screw for all the axes, not just for Z-axis. And for the belts, we are using stepper motors, and the belts are connected to the shaft of these motors with a kind of a pulley, and it becomes much cheaper, as I mentioned. But for the lead screws, you need to have a servo motor and some drivers, some special drivers of such servo systems. And again, this will increase the cost of such plotting, or we can say horizontal motion systems. And another issue about these drives, they should be quite powerful so that the system will be able to move the head on the table easily. And another issue, we shouldn't have any backlash. This is sometimes inevitable, but you should be able to eliminate it as much as possible. Otherwise, since we have many back and forth motions on these printers, if you have backlash, then some of your layers might be shifted. Some regions will be printed on an, let's say, different region. We have actually a bit different position control system. This is quite popular on 3D printers. It's core XY approach. They're not directly actually using a motor for X motion, not a single motor for Y motion. they use again two motors, but the overall motion is obtained with help of the motions of these two motors. So you cannot say that this is an independent Y axis or an independent X system. They are dependent, but if you control them properly, you can obtain any motion. And the thing is that it's much faster. So that's why people are using such an approach. Now I will show you this one. And I need to first obviously share it with you. Yes. This is just a manual operation, but it's showing the fundamental. As you see, while moving these two axes, you are only moving in one direction. It seems a bit complicated, but the advantage is that it's much faster. So if you just move one axis, it moves in a diagonal manner. For linear motion, you need to move or rotate these two motors at the same time. So due to these speed actually advantages, 3D printing companies actually preferring to use Core XY systems on their printers. So here is an example pattern. Example, let's say slice. This is the outer of the slice, and then we have infill pattern. So here is the question: which one in which region we can use higher speeds, and in which region we should use lower speeds, and why? Any volunteer?
Hocam, in pattern 1, we can use higher speeds because it's a longer streak of lines. But I think in pattern 2, going at high speeds would cause too much vibration.
So you're actually considering just the speed to determine, to give an answer to this question. You say that if the pad is longer, then we may increase the speed, but if the pad is shorter, you say we should use slower speed. But actually, we determine it according to the quality we want to have at the end of the print. Since once the print is completed, we will not be able to see the interior of this part. So the quality for the interior region is not an important issue for us. That's why we can use as much as high speed at the interior region, but for the outer part, it's better we do it as slowly as possible so that you have a smooth contour. Since after the print is completed, we will only see this dark blue region, but not the light blue region. So that's why for outer profile, we can use higher speeds. For the interior, we should use, did I say higher? For the outer profiles, we should use slower speed. For the interior, we should use higher speed. So why do you think we have 3 different patterns here? Why not a single pattern?
Outer pattern'ın shape'inden dolayı mı hocam?
Yes. Another question, do we prefer to have a single one or many of them in the interior part? So which one do you prefer? If you were a slicing software, let's say, if you are a slicing software, do you prefer to have a single pattern inside or as many more?
Single pattern would be better, I think.
Yes, it will be better since you will not need to do any stopping the extrusion or restarting it again. If you have a continuous pattern, then that means you will start the extrusion, then complete your task, and then at the end of that pattern, you will stop the extrusion. But if you have 3 of them, then what you're going to do, you will start, stop, start, stop, start, stop, which means that you will spend more time, and also the quality of your overall print will be less compared to the case where you have a single pattern. So in 3D printing inside extrusion-based systems, we always prefer to have as continuous paths as possible. But obviously, if you have such a zigzag pattern, it's not possible for the given shape. But you may have maybe a concentric one. If you have a concentric infill shape, then I think you may have a continuous pattern. So now let's have a look at another phenomenon, another stage of extrusion-based systems. We said that after the material extruded, it should be bonded to the previous layer, or it should be bonded to the table. Bonding is highly important. It's especially important for the first layer. And we did have a little problem at the beginning of the sprint. It wasn't going fine, but later it managed to stick to the table. So the thing is that you should give the required energy to the system so that its temperature will be at defined values, and it will be able to stick to the previous value. If you give too much energy, then that means its temperature will be too much. Probably it will switch to the liquid state, and you will not be able to control the material. On the other hand, if you give less energy, then that means its temperature will be less, and it will not be easily stick to the previous layer properly. It may just touch it, but may not stick, and the bonding may not be as good as we want. So this sufficient energy is highly important in this extrusion-based systems. Otherwise, if you have less bond between the layers, then with maybe a shear force, you may easily break your part into some smaller parts. But if the bonding is fine, then you'll not be able to remove that layer. Yes, this is what I mentioned. These are the same things I discussed a moment ago. Any questions, guys, about the bonding? This is, as I said, an important part of extrusion-based systems. So now let's have a look at support generation. So we said that in additive manufacturing system, we are printing highly complicated products. And the thing is that in such cases, we need to use support structures. Otherwise, the extruded material will fall, and you'll not be able to keep that material in place. So for that purpose, we need to support such overhanging regions by some extra material, extra structures. And for that purpose, we may use similar support materials, like in this bunny case. The same PLA material is also used for the support structure, or the one we are printing right now on the printer. We are using the same material for the support structure. Or you may use some secondary materials. This time it will be much easier. You may easily remove it, and if it's let's say water soluble, you can simply put your product into a water tank, and you can maybe remove these support structures in and out. So what is the rule for the support structure generation? In extrusion-based systems, we are usually assuming that if your overhang angle is less than 45 degrees, I mean, this is the overhang angle. If this is equal to 45 or less than 45, then you don't need to have any support structure. But if that overhang angle, this is here, if this angle is more than 45, then that means you need to support your material underneath. You need to have some special structures. This is actually done with the help of support generation. Here you see some letters, and they are printed in that configuration. Obviously, you don't need to print it in such a configuration. You may simply lay them down and print without any support structures. But here we are trying to show you the fundamentals about support structure. That's why we are printing them in the vertical orientation. So if you look at the Y letter here, still we are using support structure, but if you are fine with that angle, you may even not use support structure like it illustrated here. If it's around 45, less than 45, you don't need to use support structure. But for such a bridge here, this is called a bridge between two columns. Obviously, it's better you use some support structure. But there are some cases, if you adjust the setting properly, you may overcome using such support structures. But for most of the time, we prefer to use support structure underneath these bridges. And if you look at the T, letter T here, we have two overhanging regions, and for sure, we need to use support structure underneath. If you don't use support, here you see you have such a mess underneath these overhanging regions, and you will not be able to use it in your application. Here's another example. We have such a column, such a C shape, and obviously after that point, the angle is more than 45, so we need to have support structures underneath. It's another example. We have a sphere in this cube. Since we want our cube to move after the print is over, we need to have a support structure and want to remove it once the print is completed. There's another type of support structure generation. We usually have accordion type of support structures, but there are also such tree-like support structures. Their aim is the same. With the help of these, let's say, leaves and parts of a tree, we want to support these overhanging regions. But this is the most common way. We want to use accordion-like structures for most of the time. Any questions, guys, about these support structures? Why do we need to generate them? What are the advantages?
Hocam burada bu iki farklı support structure şeklinin birbirine göre avantajı, dezavantajı ne olabilir?
I will discuss it in a moment. Now our part is ready, as you see. Yes, now we can simply remove it. Yes, here it is. I think we later change the settings, but we don't have right now any support structure, no problem. I can give this toy to the guy actually who is going to do the best on the quiz, which we are going to have maybe in 10 minutes, okay? So let's go back to your question. You said that which one is better. This one is easier to remove it, but the problem is that, as you see, it's just supporting the overhanging region from some points. It's a kind of a point-wise support, but if you look at it, this one is a line-wise support. So that's why for most of the time, we prefer to have such a case. Another thing, this one is also difficult to use, difficult to fabricate, especially in extrusion-based systems. But if it's an SLA stereolithography, next week, I think we will be able to start stereolithography. In stereo systems, we prefer to use like tree-like support structures. But for FDM, for FFF, for extrusion-based systems, it's better we use line-wise support like accordion structures.
Hocam Ufak bir şey olabilir mi burada kullanım alanına ve amaca göre support seçimi? Çünkü support'u da remove ederken sonuçta yüzeyde bir kalıntı bırakması ve yüzey bozukluğuna sebep olması mümkün. Dolayısıyla yüzey kalitesinin yüksek istiyorsak tree type seçmek, işte çok önemsenmiyorsa accordion type seçmek gibi.
Yeah, it will depend on the actually part you are designing, on the type of application you have. After some experience, you should be able to decide yourself. But your friend pointed out that surface quality is highly important. You see, if you don't have any support, this will be the quality. Or if you have, even you have support structures, you will have some scratches, some marks underneath these regions. So the best thing is actually not to use any support structures. So while designing your part, you should always consider the support structures and try to eliminate any support structures in your fabrication stage. Now I want to show you, and this example I showed you a lot. Let's watch a video about it.
This is the Ultimaker.
Let me share it first and then we can discuss.
Three, a professional yet accessible 3D printer with reliable dual extrusion.
So I already mentioned these, so I'm skipping.
Temperature required. Effortless. For that, plate and the knob. Build plated and material.
These are the same things I discussed a moment ago. Yes.
Complexity.
Here we go. Now it's
materials.
Printing this gyro thing, and as you see, there are two different types of material. This is built material, the one actually you want to have after the part is fabricated, and this white material is the support structure, and we don't want to have it after the part is finished. And as I mentioned, this is water soluble. After part is ready, we will simply put it into a water tank, and they will be sold. And you see that it's using two nozzles. This is responsible for the gray material, for built material, and the other nozzle is responsible for the support structure material, which is PVA. This is how it goes. Now it's switching the nozzles. Oh, this one is went, and now we have the second one. These are the materials, the built material, gray one PLA, and this is PVA. This is water soluble. Now it's about to finish. It's showing the fans. We have 1, 2, and 3 fans in that head. Yes, now the part is finished. So this is how we are removing the support structures. Yes, now we have the complicated shape, this gyro, and it's fully functional, like the one I have here. And you cannot print this one or fabricate this one by using any conventional type of manufacturing technology. You can only do it by additive manufacturing systems. These are some other examples. It has dual nozzles, so we can print parts having 2 colors. Any questions? Okay, let's move on. We were discussing some support structures. Now let's discuss plotting and path control. And the paths are generated, as you know, in the CAM software, in Cura in our case, and by doing some settings, you can adjust the amount of infill, you can decide on the layer thickness, the number of shells, so all these properties are set within the CAM software. So the path is quite important, since if you do not have material underneath that layer, you will not be able to join that extruded material to the previous layer. So your CAM software should also be aware of the previous layer and have a proper connection between the consecutive layers. And if you want to have an accurate part, it's better you usually print at lower speeds, but for the first layer, first few layers, maybe you set the speed to a lower value and try to make sure that your part is stick to the table properly, and then in the upcoming layers, you may continue increasing the speed. Another issue is that while printing the shells, let's say, it's better you have little overlap between the extruded beads of material so that the strength of your part will be much better. So the most difficult part actually for the CAM software is determining the infill pattern. Generating such patterns, making it as continuous as possible. These are the most difficult parts for the CAM software. And another issue is that we want to have some shells. If this is the part, then we need to have usually another shell inside. As I said, the strength will be improved. And it's very similar to having some pockets in the milling operations. And we don't have a specific solution for that. We may have numerous type of infill patterns depending on your settings. As I mentioned, you should have as continuous as possible so that the quality will be much better, and in a shorter time you'll be printing the same product. Another issue is that it's better you have different patterns at consecutive layers so that your overall strength of the part will be better. If you have exactly the same pattern, then it's easier to break it into parts. So we usually prefer to have different patterns in the consecutive layers. And the extrusion on this extrusion-based systems obviously depend on the pressure you are applying, the temperature of your nozzle, the diameter of your nozzle, and the material, the viscosity of your material, the flowability of your material, the gravity will obviously affect the extrusion process a little bit, and other temperatures actually building up in your part. Since you may have a closed region, the temperature of that part might be a bit higher, and you may develop some thermal stresses inside.